In this lecture, we are going to talk about automated mechanism design. First, I want to give a brief overview over what automated mechanism design is and why it is a useful paradigm. The basic idea behind automated mechanism design, or AMD, is that you can see the problem of finding a mechanism for a specific scenario as an optimization problem. This change of perspective has several advantages. First of all, it is flexible and can be applied to a broad set of problems. Second, it makes a better use of problem-specific information that are available to the designer and are usually not taken into consideration in classical mechanism design. Third, in terms of efficiency, it shifts the burden of finding the actual mechanism from humans to a machine. When dealing with an automated mechanism design problem, we are given the following setting. There is a finite set of possible outcome x and a finite set of agents n. Each agent has a probability distribution over a finite set of types and a utility function associating to each pair, type, outcome the payoff of the player. Then we are given the objective function that the designer wishes to maximize. On the basis of this objective function, we can distinguish between a benevolent designer who wants, for example, to maximize the social welfare or the minimum return of players, and a self-interested designer that wants instead to maximize her own returns. In the following, thetas in bold will denote vectors with one type for each player. We consider the following problem. Suppose that a couple is getting divorced and that they own a valuable painting. An arbitrator has to decide what to do of the painting. Specifically, she has 4 possible choices. So the first possibility is giving the painting to the husband, then give the painting to the wife, establish a joint ownership of the painting and place it in some museum, or, which is kind of an extreme solution, burn the painting and destroy it. The data are the following. The players are the wife and the husband, and they have 2 possible types. Type low, which means not caring a lot about the painting, and type high, which means being very attached to the painting. Each player is of type low with probability 0.8 and of type high with probability 0.2. Then you can see the matrix associating a payoff for each pair type outcome. This is the first problem we want to solve. There's a benevolent arbitrator that wants to maximize the social welfare of the players. The problem is that each player, even if of type low, will prefer having the painting over not having it, and therefore it is not trivial to understand players' true types. Our goal is designing a mechanism which is bias-Nash incentive compatible and guarantees ex-interim rationality. In this setting, we don't allow payments, and we want to have a single final outcome function G. The problem can be solved with this formulation. The objective function is the social welfare subject to the choice of G and the type's probabilities. Then the first family of constraints enforces bias-Nash incentive compatibility. So we want that telling the true type is at least as good as, in expectation, to reporting the other type, the other possible types. The third family of constraints is for ex-interim rationality, and then variables in G have to be binary and we have to select exactly one outcome for each pair of reported types. This is the mod file that encodes the formulation we just saw. We have a set of types T and a set of outcome X. Then we have two utility matrices and the two probability distribution over types. Then binary variables G are defined. Then the objective function maximizes the expected social welfare of the two players. Then we have the first family of constraints, which enforces Bayes-Nash incentive compatibility for the two players. The second family of constraints enforces ex-interim rationality. And finally, we force G to sum to 1 for each pair of reported types. The DAT file is as follows. There are two possible types. We'll denote type low with 1 and type high with 2. And there are 4 possible outcomes. Outcome 1 is when the first player gets the painting. Outcome 2 is when the second player gets the painting. Outcome 3 is when the ownership is joined. And outcome 4 is when the painting is destroyed. Then we describe the two utility matrices indexed over outcomes, so rows, and types, so columns, and the types probability vectors. This is the round file, and notice that since the formulation is an integer linear program, we can employ Groby as the solver. This is the result that we obtain, and in this case the arbitrator will select the joint ownership, so outcome 3, for each pair of reported types.